Yeah. So today we are going to talk about paper which came out probably last week, QLoRA. And at least I would say like the interesting factor of this paper is like how to efficiently fine tune large language models and like probably of this much higher scale than what we were able to do before. And in terms of the memory requirements and things, like you can just fine tune like a very big model of banana as well. So, so I think that's where this approach, or at least shines a lot higher. And yeah, so as per the paper, they were able to like basically they show different models ranging from like a 7 billion parameter to 65 billion parameter scale, and they can fine tune that on a single 48 GB GPU, which is like comparatively, if you look at like when you consider like a LoRa or whatever fine tuning setup that you will consider, right? Still, in terms of that also, the memory consumption is very, very low. And the main advantage of this approach, or at least I would say the key aspects of this paper, are like how to efficiently fine tune using 4-bit. So not exactly 4-bit, but like we store this like model into 4 bits, and then basically let's say do the operations in 16-bit. So yeah, like effectively when you're storing, you are just like basically having this 4-bit return model, or at least weights, so which kind of like significantly reduces your memory consumption. And they release a model named Guanaco, like which is built on top of Llama, and it is a fine tune on instruction tune data sets from different corpora and publicly available ones. I think Open Assistant and Plant V2 mixture, and based on that, they like get approximately 99% performance on the benchmark. And just to give you some numbers or trends, like they were able to fine tune this model, like I see the bigger model, like a 65 billion parameter model with this like 24 hours like on a single GPU, and you can just get really good performance. The key aspects of like this 4-bit are like three things. So one is a 4-bit normal float, that a new data type that they try to have propose. Next is a double quantization, which kind of significantly. So what you do in this case, you apply quantization on top of quantization, which like again reduces memory consumption. And the third is page optimizers. The essential concept of page optimizers is some sort of a memory mapping, right, or paging, which effectively enables you to like move data to and from GPU like easily. And yeah, feel free to interrupt in case of any questions. And as I mentioned, they get like state-of-the-art performance on like high quality instruction tuning data sets. So yeah, that's about it. One thing, if you look at like basically, let's say why this paper itself is important or at least useful, right? So just to give you a benchmark or at least some numbers, right? So if you let's say pick out a 16-bit fine tuning of like Llama, right? Like a 65 billion parameter. Okay, sorry. Is it now clear or? Is the audio clear or yeah? Okay. Yeah. So the main advantage of this approach, or at least why I would say this approach shines a bit more or has more impact in terms of like usages, if you consider the standard fine tuning, right? Basically, most of the literature people fine tune on 16-bit, yeah, like do a 16-bit like operations, right? Basically, when fine tuning. So if you do a 16-bit fine tuning of the standard Llama model, right? Basically, 65 billion parameter model, then the total memory consumption is way, way higher. So which is 780 GB of GPU memory, right? So which means you cannot like do this fine tuning on a single GPU. You need like basically probably like 800 cluster, right? At least to so do this sort of fine tuning. 800 node basically. So the way they are able to like bring down this memory consumption is something like really of interest. And while also like bringing down this memory consumption, right? Ideally, you would assume that basically, let's say you do it back and forth, like moving the data, right, to and from CPU and GPU, right? But eventually, even if you do that sort of small operations, the overhead is not much, and you can still get the nearly the same performance when even if you're like when basically storing it on a more compressed fashion. Yeah. So Yeah, this is something I don't expect. Yeah, so if you look at this, so from 65 billion parameter model, like it contains like a 780 GB memory to like 48, less than 48 GB memory. That's a very significant reduction in terms of the memory. Like, so if you roughly consider, it's probably like 188, like in terms of, no, not 18, sorry, 160. So that's about this. And next thing, yeah, but one thing to note, if you look at this is just the numbers, we'll probably explore this more later on. But based on the numbers that we see, right, in terms of the LO ratings, so LO is a rating that is used in chess and many other sports. And what the rating essentially tells us, let's say, if a it tries to compare the skill sets of two players, and based on the related difference, it tries to say like which has like a expected win rate, higher win rate, right? Like you see than the other one. And if you look at this, right, like Bard is relatively uh, way behind like the other competitors in this, and Gunako based on different like scales, you can see like the ratings on like at least like they outperform Bard and like are near to GP4 at least. And in terms of the memory consumption, you can see like it's the 7 billion requires a 6 GB memory, whereas others like as you scale up, like overall memory requirement is still comparatively lower than the 16-bit standard fine-tuning model. Sorry. Yep. And as I mentioned, they fine tune on the Open Assistant dataset, which is a dataset of multi-turn dialogue instructions, or at least some feed based on RLHF feedback. So they just consider that dataset and they find that that outperforms the FLAN mixture that was released by Google on MMLU tasking, many more other benchmarks or something. Okay. Yeah, and also one of the other highlighting factors, they even do a comparison about like human rating as well as GPT-4 rating, and then present some evidence about that as well. But in this case, for like more qualitative analysis and things, they also do like a rating where GPT-4 is acting as a judge and also human acting as a judge. And in both cases, they find nearly the same trend levels. Yeah. So overall, the diagram, like figure one that we have, right, that kind of uh, like pretty much sums up the idea. So if you look at like on the left side, right, this is where we do full fine tuning. You operate in a with a 16-bit transformer. So whatever the base model you have, right, and let's say you store optimizer state in 32-bit. So when you backpropagate, you still like basically uh, like store everything, right? Activations is like stored in 32-bit or 16-bit activations, right? So overall, you're still storing way more, and you require more memory. When you do, let's say LoRa, right? Like in LoRa, maybe you just update like a handful of parameters, right? But still, since like for updating those parameters itself, right, you need to store the intermediate like activations, right, and cache it when you basically and like later on do a backup, like so. So the activation gradients that are there, right, those are still basically in 16-bit, and which is why the computational memory like goes a bit uh, higher in this case as well. Or even though like you would let's say just fine tune like a very handful set of parameters compared to. And when you consider the QLoRA, you can see that they have a 4-bit transformer where let's say you perform some operations, then you like delegate that to different adapters. Once you have the adapters, then you have the small page optimizers, and where there's a CPU offloading happening to and fro memory transfer. And based on that, like we then back up the gradients and all. So overall, you can like manage to do very fine tune like a very big model with like a single GPU itself. Like. And the main advantage of paid optimizer is to like in case of very bigger models, it just like does like a transfer between CPU and GPU like effectively, like the optimizer state. Yeah. So now coming to slide background. So blockwise k-bit quantization. So at least for on a broad level, I would say quantization is nothing but like you can think of this process of like let's say compressing the information, right, or at least like representing the same thing with very let's say less bits, right? Or at least that's sort of what quantization means. So when you try to represent something in less bits or at least approximate this, right? So you lose out some information or at least you do some approximation, right? So that's like, so for example, maybe like you have a 32-bit like float, right? But then you want to convert that to 8-bit integers. So you might have experiences when you use like or load any bigger models, right? Basically for inference, like in 8 bits and all. So the results might not be deterministic, but eventually you still like retain or at least get the nearly the same performance. And the way typically quantization is done, what you do is like, let's say, suppose you want to like restrict or quantize to some ranges, right, that you want to operate in. So what you do is like you take a round of like, let's say the range that you are operating in, like the maximum value, and also divided by the actual max value of the integer, like basically the tensor that you have, right? And you just take a scale it up. Like so what you are doing is essentially you're just scaling up, right? Basically in a way, like all the inputs that you have. And that's how you're in this case the notations are. And your C of FP32 is nothing but like a quantization scalar, right? Like basically, which determines how much like my input should be scaled. And when you want to dequantize, like something you just like basically divided by the actual int or a quantize the quantity that you have, right? Like quantize input. But one disadvantage with this approach might be, let's say, if you think of taking out like an absolute, right? In this case, maximum. Suppose you might have some very large magnitude values, right? Like in certain tensors, right? Or at least certain bins, right? So if you just take or apply this uniformly across all the bins, right? Like you see, then it might not effectively like capture, or at least you might not have more uniformly sampled bins, right? Or at least some grid. So as a way to fix this, or at least measure, what typically what we do is like we just split the actual integer, or at least like the number into different blocks, and then we apply like quantization on each block separately up chart. And that kind of leads to more better and like effective way of quantization where we do not suffer with the problems of outliers. And now coming to LoRa. So LoRa is a way to fine tune the model. So what essentially it does is it initializes a set of parameters using low rank matrix approximation. And then basically it just adds that as a component similar to adaptive specific. So if you look at the diagram on the left side, right? So what you have, like you have, let's say, a pre-trained weight W, right? And essentially like you want to do a low rank approximation or add a very small number of parameters, right? Like for fine tuning a language model or whatever the model of choice. So what you do is like you just perform a low rank matrix approximation for this W. And let's say you get like the smaller components like A and B, which are comparatively much smaller. Once you have the smaller components, you just like you see treat this as a separate branching factor. And in that setup, B is initialized as 0 and A is initialized with a normal distribution like with mean 0 and like variance sigma. That's it. A standard deviation sigma. Variance. And what your computation looks like is where you, let's say on the left side, you just like multiply the input with the weight. Like I see that's a linear transformation that you do. And on the right side, you basically have this like a scaling factor S times like you do a linear transformation, right, of the input. And once you have this input, right, you just apply a non-linear activation on top of it and like basically do it like forever. And you do it for each layer. And the standard LoRa setting was like applied on like where you did this on like the query and key attention system. Now, in this case also, if you look at right, the memory footprint again for LoRa, although let's say it might be just like maybe like 1%, 1 to 5% of the entire network, right? Basically the number of parameters you might update. But still you store all these activations like in 16-bit, right? Like as a cache, right? And basically when you backdrop, like your computation still increases, right? Like in this setting. So in order to, let's say, get an idea, right, about this, like how much the computation grows or like how much like the memory requirements are. So for example, like when you consider 7 billion Llama model, when you try to fine tune or basically train that model on a flat V2 mixture with batch size of 1, the typical parameters that you update are point to roughly 0.2% of the original, but the memory input gradients memory like grows up by about 5-6 VMD. And if you look at like on an average, the actual parameters only take about 26 MB. And when you like, so since now you're operating with very big models, right, and you're doing this batch size of 1, so you usually like do a gradient checkpointing, right? So when you do this gradient checkpointing, so overall effectively you can think of this, the average uh, memory requirements per gradient operation is like per gradient surface basically 18 MB per sequence. And yeah, and similarly, when you look at like this 4-bit base model, right? So overall, you will be consuming about 5 to 6 GB in memory. So you can imagine like by just storing the weights and like this 4-bit, you can significantly reduce the memory requirements of the model. Eventually. And what you do in this case is you just like do some sort of like quantization and dequantization when you are trying to do some multiplicative operations. Yeah. So now, like, we'll actually look into the details of the actual method and the different data type operations that they propose. So just to make it clear before we start that, like if you look at right, like QLoRA has like one low precision storage data type, right? Uh, that's 4-bit, and the computational data that we type that is there, right? We usually do like it's a batch float, right? Like we brain float 16 that we do operations in, right? So that's like the consistent notation that will be throughout. So storage is done of the model parameters in 4-bit and operations are done in 16-bit. Yeah. So far, any questions?
Hey, Jay.
Yeah.
This is a really good talk. Thanks very much. So when they talk about this n-bit or 4-bit for QLoRA, does that mean that the precision of the weights are 4-bit also at the end of the process, or is it something else that's happening?
So I think the precision of weights, I think, are 4 bits. So it's not even though let's say you do this right, like yeah, precisions of weights are 4 bits, but like operations, whatever you do, right, you still like then convert them to 16-bit and like do operations. So if eventually what you store is just 4 bits, yeah.
And as a consequence to that, that means that at the end of this process, the model is a 4-bit model.
Yeah.
It's not like you do a final sweep of 16 bits just to like try and get somewhere closer to the original or anything like that.
Yeah, it's a 4-bit model because they store
Okay.
it in special data type, right?
Okay, thank you very much.
And yeah, so this 4-bit normal float quantization, right? So essentially what this tries to like at least do is like ensure, let's say, that the quantization bin has like equal values assigned. And this is pretty much inspired from information theory, theoretically optimal data, like information theory bound information theory, I would say, and where they try to propose a information theoretically optimal data type that at least like ensures like the quantization bins has equal number of like values, right, in each input tensor. And when you try to do this quantization, right, like you see it, in this case they do this estimation of the quantization, like estimation by considering empirical cumulative distribution function. And typically if you look at like this process of quantization, like estimating quantization, right, for quantization, that is very expensive. And there are several approaches for, let's say, approximating this and maybe speeding up the process, right? One is SRAM quantize, but they itself like have some limitations and like suffer from large quantization errors for outliers. So overall, goal at least of the authors is to still reduce the computational costs of this doing this estimation, but like getting as much precision as possible. So as an effective way, the authors try to do is like basically fix a tensor, like make assumption that the input tensors come from a distribution fixed up to a quantization constant. And when you do this assumption, right, you can basically now approximate this calculation and like do it more effectively. So by this way, by this simple assumption. And this is also, I would say, at least possible in context of neural networks, because if you look at the neural networks, right, the way we initialize the model or at least the parameters are, right, those are mostly like centered around zero, right? So you can consider that as to be very similar to like a weight matrix based on like similar to a zero-centered normal distribution with some deviation, right, delta or like sigma in this case, suppose. So eventually, when you let's say want to do a quantization to a fixed quantization constant, right? So what you do is you just transform the weights, right? Basically by shifting the distribution, right, or scaling, like basically the values, right? So that's how like they try to do it, and legacy proposes data type. And suppose for example, in this case, if you look at like the uh, for example, like if you consider like in this case, like throughout the paper, they try to restrict it to be between -1 and 1. And like in this case, it's just like a scaling up, like I'm trying to ensure the values. And for example, now like this process follows 3 steps. So one is like first you estimate the number of bins or the quantiles, right, that you want to have. And when you are doing in this case, like let's say for a k bit quantization, right, there would be 2 raised to k plus 1 quantiles. And all of this are between like this, like drawn from a normal distribution, right? Basically between with mean 0 and deviation of 1. That's the first part. Second is once you get this distribution, right? Now what you do is you normalize its values, right, to be between -1 and 1 range. And third is you done quantize the input weight tensor by normalizing it again into like between -1 and 1 by doing a maximum scaling, right? Like rescaling. So that's how this process at least works. And the formula for this process is given as below. So if you look at basically for doing a quantization QI, right, basically in this case for a value, it is nothing but half like times like a quantile function of the standard distribution, where let's say you have like some value I, and basically you have total of 2k plus 1, 2 raised to k plus 1 quantiles, and you add like another next adjacent term basically in order to avoid symmetricity. Yeah. So I think the main argument for like why we don't want symmetric k-bit quantization is that it does not have a representation of 0. So which is important when let's say we want to pair the things, right? Like or at least like quantities and other non-zero elements as well with no error, right? So in order to like do this, what authors do is like they just have like create this quantization discrete, sorry, asymmetric, by adding quantiles like qi of 2 ranges. One is between 2 raised to k minus 1 for the negative part, and 2 raised to k minus 1 plus 1 for the positive part. And by doing this, you might have 0 on both sides, so just remove 1 0. Yeah, but I'm not sure I completely follow this part, but yeah, this is like how they try to do it. If anyone has any better explanation or idea, then you can probably pause for a while if anyone has any better way of explaining, like if they follow this. Yeah. So maybe I'll move on. But yeah, this is something I'm not completely sure about, like why they need like why for at the first place like the quantization is like symmetric, and like why it is not asymmetric. But yeah, like this is something I'm not sure much about. And next is double quantization, where the underlying processes, like let's say you apply quantization on top of quantization, So let's say in quantization, you are still operating at smaller scale, right? And then we see on top of that, you apply another like level of like round of quantization, which even drastically reduces the memory usage. So for example, if you consider like a 632-bit constant, right? Like, and let's say you have a block size of 64, right? For your weight matrices, quantization constants add roughly, you can just divide it by a factor, right? 32 by 64. So which means like 0.5 bits per parameter, right? Basically of a weight matrix on an average. And if you want to still even reduce this further down, so what the authors in this case do is like they apply quantization on top of a quantization constant. So like we had seen uh, this quantity, right? Where yeah, so where let's say this is a quantization constant, right? Like that we have like a where what the authors do is like just this rounding of factor, right? Like of the original term, which like the ranges by the maximum value that it might incur, right? So in this case also the authors do the same, but they apply another round of quantization. So and they term it as like a C2FP32, and this acts as an input to the second quantization. So the second step, if you look at right, like you see now, like the second step that yields a quantization constant, right? And that is known as C1 FP30, FP32 in this case. So essentially what they do is like they use a 8-bit float with a block size of 256 as a second quantization step. As and when they try it, they observe no performance degradation for this 8-bit, like, and this is I think like we're probably already shown in some uh, for precursor paper of the same authors. And like if you look at this, so the overall memory or bits, right, that you require, like reduces by a factor of 0.32 with respect to this weight. So the overall computation looks as 8 by 64 plus 32 by 64 times 256, which is again, I'm still not sure how this computation goes, or at least like works. Maybe I'll need to dive deeper into that, but essentially I'm not sure about like where the 64 at least comes from. If it's just 256 and you apply this, or it's like maybe follow up like, which is why you need like again a reduction factor. Yeah, so that's something, yeah, I need to like this is check in more detail, but yeah. So the overall now the bit requirements are just 0.1 to 7. The next another thing that maybe essentially which makes it just happen, right, is page optimizers, and this is probably to do with the NVIDIA. And NVIDIA has some like functionality of like doing a unified memory mapping, right, between uh, CPUs and GPUs for effective transfers, so that there is no error on GPU when you process the data. So they make use of that and basically integrate this feature, and which makes it like the requirement, or at least 4-bit optimization, like this fine-tuning possibilities with the storing of this weights. So essentially, when you're, let's say the model is very big, you don't store all the optimizers like state in the actual memory. You just offload something to CPU and then just load back into the memory when convenient. So overall, now if you look at the overall like the way the pipeline works, or at least a formulation is, right. So what you do is like let's say it's similar to LoRa, where like what you do is like you have this batch brain float 16, right, the input in this case, and now you do this. Yeah, so this can be treated as nothing but the same W from the original one, but in this case you do a double dequantization of the W, since you're storing it into the 4 bits, right? So when you do the operations, you need to map it back to the 16 bit. So you do a double dequantization. And next thing again you do is like brain float like 16 of this input, and you have this adapter parameters which are 16 bit. So which is like L1 and L2. So this is how you do it. Like, and overall, one thing I'm not very sure, but like which I do not follow or maybe like properly understand is the in the fine tuning setup, they don't actually like put this and this to 4 bit, which is very weird, because if like they are able to do like put a reach and weight into 4 bits, right, then essentially this itself might have been possible, but not sure what's intuition or rationale behind that. But yeah, just one thing to point out. So if you look at this, and like overall, it seems like once you have everything trained, right? So while training, you cannot like see do this section like compromise a bit precision, right? At least if you consider like why authors do not like put this into this two quantities to 4 bit. So which means like while training, you do not want to compromise on your precision, right? So which is why you still remain to the same. But once the parameters are trained, you can still like offload everything to 4 bit and maybe do the calculations. So that also presents an interesting use case in terms of like inference. Maybe this might be possible to just do this in 4 bit. Um, yeah. So for experimental setups, so this is how this overall setup or at least the method or process was. Any doubts or any questions so far with respect to how like this storing of 4 bit weight is possible, or at least yeah. And for doing this, I think they have to write their own CUDA kernel. So for backprop, so yeah, just to so now in terms of the experimental setup, like they try across this 3 different architectures: encoder, only decoder, and encoder decoder models, and like try and like compare like the effectiveness of QLoRA with 16-bit adaptive fine tuning. And overall, they consider 3 datasets in this case. So one is glue, other is supernatural instructions, and third is MMLU, that is 5-shot MMLU. And if you look at this, right, like overall in terms of most of the models that you will fine tune, right, if you have 16, like 48 GB GPU, right, like or 24 GB, you might not like need page optimizer, or at least there won't be like much harder constraints for that, right? But when you have very good bigger models, right, that's where like page optimizers might be of use, or at least like so they do provide some analysis, but overall I think it depends on different model parameters and yeah, yeah. And as for the studies, it seems like it just like requires the same training speed as the regular optimizer. So even though there's some latency, but still you can like manage to train like the models on the same at much lower memory like cost storages. And and also one more interesting finding is like the standard LoRa parameters, hyperparameters that are there, right? Which you use for 16-bit fine tuning, or at least that do not work well in this setting. And what they essentially find is like you need to do a full, like you need to add more adapters. Like so, the number of adapters like needs to be higher in this case across each transformer block. So for getting a like matching the performance in this case. And next thing is 4-bit like normal float, like the data type that they propose, right? Like which is information theoretically optimal. Yields better performance than the standard 4-bit floating point operator. And if you look at this, right, this particular figure gives you the so the blue line that is there, which is like a float 4-bit, right, 4-bit float operator, and the orange line is like the normal for normal float 4-bit normal float. And when you like apply like a 4-bit normal float plus double quantization, right, like you are still nearly the same, right, in terms of the performance, and your bit requirements are a bit low. So yeah. And in terms of the absolute numbers, yeah, this is what we have. So if you look at the info, right, that we have, our mean perplexity is about 34.34, and for others, like you still do much better. So yeah, and like this is the one where it is way cheaper, like small. It is in the better best. Apart from that, like when you do this k-bit LoRa, QLoRA fine tuning, right? That effectively matches the 16-bit full fine tuning that you do. And here are the numbers for the same. So if you look at this table, right, like basically it presents the numbers on 2 benchmarks. So that is glue and the supernatural instructions. For glue, we have accuracy, and for supernatural instructions, it is root L score. And in both cases, you can see that even like with QLoRA and normal float 4 plus double quantization, you still like do the same. Like there is no performance compromise at least. Like, and effectively your memory sizes or requirements will get reduced. And next thing again, when you look at the MMLU as well, right? 5-shot MMLU, you can observe like the same thing, where let's say you have different model scales, right? 7 billion to 65 billion. And you do this across batch float, brain float 16, B float 16, float 4, and NF normal float 4 operation plus double compilation. And you can see that like effectively you do as good as like the B float 16. So yeah. And now in terms of like the data sets, like further they also try to study like how, let's say this works in terms of like chart applications. So they do analysis about that areas. And in that case, they consider two data sets, two primary data sets, but I think there are many more other data sets as well in consideration. So I think like total it is 8, and the main data set that you find out to be useful are Open Assistant 1, that is there, and the Flan V2. And in this case, they just do a standard fine tuning. They don't introduce any RL objective to actually understand if like whether the gains come from which ways. Like if it's like the RL like HF objective or probably like the like avoiding confounding factors. And for certain data sets, there might be multiple responses. So what they do is they just select the top response of each entry level of the convolution tree and like fine tune the model on the selected like full selected convolutions, and they include instructions as well. And in this case, for the chart applications, they compare like models such as Vicuna, Open Assistant, GPT-4, GPT 3.5, and BART. And overall, if you look at table 5, right, like I see that is there. So if you look at, they try like the QLoRA fine tuning and evaluate on MMLU 5-shot with like different data sets from. So where you use like let's say Guanaco with Open Assistant and many more other different data sets, and there is a performance measure for that. So when you see like you have Llama no fine tuning, and compared to that in Guanaco one with the Open Assistant fine tuning with the Open Assistant data set, you tend to perform a bit better. And yeah, similarly they try for others as well. And for we'll just start with this particular one. Table. So if you look at this table, so this table shows the performance of Guanaco models on which are fine-tuned with like QLoRA approach, like that is base approach, and like they are fine-tuned on OSTT one dataset. And in this case, you can observe that overall the models tend to do better than other open source models available. And in this case, like there is this comparison between ChatGPT and the corresponding system, and overall average performance, if you see like in different like categories, the models tend to perform better than their counterparts. And yeah, in this case also, when you compare BARD and the other models, like Guanaco models tend to do better like than BARD. And probably I think this is also maybe due to like BARD being more very well calibrated, or at least restricted in terms of the outputs it can give. And when it is unsure, it just like falls back to like like not giving any answers. So that's sort of a consequence why it might not have like very high numbers. Okay. And also in this case, like they do human evaluation and GPT-4 rankings as well on Vicuna benchmark, and they find that the human evaluations and the GPT ratings do not seem to match or at least correlate, and partially disagree. So for Guanaco 7 billion model, but overall they see like a correlation factor of 0.43 for Candle and Spearman rank correlation of 0.55 at each system in this case. And yeah, for between agreement between human and GPT-4, I think it is a bit lower, that is 0.25, the flex kappa score, and which shows that both do not seem to agree much, but yeah, And authors say that maybe model-based approach, evaluation approach is better than this particular one, or at least useful and reliable compared to like alternative to human evaluation. And in this case, this is numbers for the L rating. And in this case, they consider Vicuna as well as Open Assistant. So Vicuna, they have 80 prompts, and these prompts are, I think, composed of. So these prompts are composed from diverse set of categories which are not modified. In Open Assistant, like it is a multilingual, multi-turn dialogue collected from crowdsourced between a user and assistant. So between different like data that we see, right, we can observe that like even in humans as well as like the GPT-4 as a judge, right, overall ranking survey stays the same. Maybe the relative scores might not match necessarily, but yeah, so that's one case to point out, and yeah, that's sort of like the evaluation that they do, and there are some qualitative examples as well which are there, and yeah, you can look at that and see. But overall, I think the model is like better compared to the open source models available. Like, and I think like yeah, GPT-4 is the best model, but after that, I think like in terms of LO ratings and benchmarks, Bunako is the best. I would say. Yeah, so that's I think all about this particular work. And yeah, any questions? Maybe. Hello.
Maybe just one. How do they use the GPT and GPT-3, 4 to evaluate? Are these scores just public, or what's that process?
So you mean like how they use GPT-4 as a judge, right?
Yes, yes, yes.
Okay, so what they do is like they provide both. Maybe like LO is like a ranking between model A and model B, right? You basically want which model has better output, right? So what they do is like they prompt GPT-4 with like basically outputs from two different systems, and then ask which system is better, like or like it's in line with the question, right? And based on the like response that you get from GPT, right? They just rank like or basically assign a 0-1 score, right? And if both the responses are like equal or tie, then basically just give point for point to each. And that's how like basically they just like actually get this like basically which is better, or like which when in each iteration or like prompt which model like basically is better, and then based on the LO rating they just try to like do this, because I think they repeat it for I think probably 10,000 times, and they compare different models like so yeah, that's how they generate with LO ratings. But I think this the details are available I think on the GitHub repo about this evaluations as well. Yeah, does that answer your question?
Yeah, that was great. Thanks very much.
Yeah. And yeah, depending on like basically what your scaling factors might be really hyperparameters in the score, right? So in this case, like a 10-point difference between like two systems indicate like a 1.5% chance, like higher chance of win uh, between system A and system B. So any questions? Apart from that, there are some other, I think, tables and analysis that might be of interest, but yeah. And overall, I think one more thing that might be of interest is like how much biases does this models have, right? So in this case, like if you have much lower score, right, that let's say it indicates lower likelihood of generating like those sequences, right? And if you look at basically when you find in Guana for right with this data sets, probably you can also like basically mitigate some bias. So yeah.
Jay, does this indicate that everybody should just be training their full models with 4 bits precision, or does it mean that it only really works as a fine-tuning step?
Right now, I think they have tried this as a fine-tuning stuff, but I think they mentioned that probably this still needs to be tried in terms of training and see whether this might like work or not. The one thing is like if you do this right, like even if you look LoRa as well, right? Let's see the fine tuning that they do, right? They still do the fine tuning in 16 bits, right? They don't touch the weights of those things, right? At least. So I think essentially maybe the main, I think, underlying based on the approaches of the things that have been followed in the paper, right? It seems clear that probably, yeah, you cannot do this sort of step in 4-bit at least. Once you have like this trained, right, then maybe you can do this 4-bit and like do this other inference, right? But I think training it in 4-bit is not maybe uh, something feasible at the moment because of like low precision, right? And like there might be training instability as well.
Yeah, I just need to think more about that. I get what you're saying. I just need to think more. Thanks very much, Stu.
Yeah. Any questions?
Okay. Any other question? Yeah.
Sorry.
No, I was just gonna ask the same thing.
Yeah.
Would it
This
be?
paper,
I think get time this week, I guess, to go through the actual code and implementation and so forth. Does it make sense for us to do that next week?
I think yeah, we can do that next week, I guess. Yeah. Yeah, but I think this paper fundamentally, I think like has more probably from actual systems and those areas where they do all of this like low level optimizations and tricks to actually make it work. But yeah,
Yeah.
it's really interesting, I would say. So, and I think partly to do with NVIDIA's like new latest updates and all, which kind of make this even more accessible, I would say.
Mm-hmm. Mm-hmm.
Yeah, but really interesting.
Yeah, then we can do the actual kind of a code walkthrough type
Yeah. I think
on our own
there is
next week.
yeah, there are notebooks available. So yeah, we could definitely like go through those notebooks and then maybe do it on a maybe some toy example or just some smaller research and see yeah, it would be interesting.
Cool. Okay, I think we're at time. No more questions on my end. Anyone else?
Yeah, any questions? Broadcast, yeah, probably I guess yeah, maybe this paper is a bit more, I would say, requires a bit more low level ideas, right, or less knowledge. Maybe that's why I think it's a bit more hard to follow as well. Even for me as well, some things are a bit more because I'm not maybe aware about those or probably yeah. So it's a way it might be a bit hard to follow along those lines. I would say. But yeah, overall the idea is still very interesting and like kind of follow up on the same principle of LoRa. So yeah. At least in terms of idea and like how it works, at least I hope that's clear. Yeah.
Yeah, I mean, we can also go through the code. It's all open source, so
Yeah.
I feel like sometimes that's easier than.
Yes, I think that would be easy. Yeah. But I think it also do more primarily with respect to, I would say, the hurdles and all that they have, because I think that's where all this like optimization fits in and like optimizations to
Mhm.
do that.
Yeah.
Yeah.
Oh, all right. Thank you all. Next week we'll try to focus on going over the code here and go from there.
Yeah. So next step will be just like spending time going over the code only, right? Or like are we thinking of
I think
something?
so. I think so. I mean, we can look over. I'll see if there's anything like, I mean, there's a lot of other papers. So if you guys want to, if you have other suggestions, then sure, let us know. Otherwise, I think this is also pretty useful.
Yeah, I think we can spend maybe time going over the code because I think it would be definitely something interesting and like a bit more, I'd say, like time consuming as well, right? Because we might like have to go through the more low level operations and but, you know, that's sort of very interesting.
Mm-hmm.
Maybe we can spend next week going over the code and maybe from the week after we can start like again like reviewing some papers. Like, that seems interesting.
Yeah, sounds good to me. Yeah, I
So
can work
is
with us on going over this. Yeah, if
I
that
think
sounds good.
yeah, I guess I might also be able to like help out on like going over the code as well. And like yeah, maybe so we can within me Akash can maybe do this. So, how that looks.
Okay, yeah, I'll ping you offline and we can decide.
Yep, sounds good.
Cool. Okay, I think that is